Hey, welcome back, College Chemistry. So we are looking at gases and how they start to move, interact with one another, and with their system or their surroundings in terms of the chambers in which we started to put them into. And so today we're looking at temperature and how temperature starts to interact or play with the speed of our particles. Now, for some of our physics people, you might remember that there is a formula for this. We know in our mathematical formula that kinetic energy, Ke, which is the energy of motion, how quickly our particles are moving, mathematically speaking, is derived from two pieces. Mathematically, it's 1/2 mv squared. And I don't want to get too bogged down by the math here, but there's two kind of variables that we should be thinking about, m and v. Our m is referring to the mass of our particles, while v is referring to the velocity. Now, think about this for a second. We know this to be a kind of physical truth as we interact with our particles around us. If we heat up a substance, that energy goes into our substance, it gets absorbed. Going back to thermal chem a little bit. And so we have one of two things change. Either the kinetic energy will change, the energy of the motion, or the potential energy will change if we are changing our phase from one state to another. Here we're just looking at our gases, our gaseous particles, and the effect that temperature and mass have on their speeds. And so we're going to be looking at the first two figures here. This is on handout 5.3. I just want to work through these, make sure you're feeling okay on these, and kind of starting to see the relationship between these three factors: the temperature, the mass, and the velocity. And so here in figure 1, we've got a bunch of different gases. We've got oxygen, nitrogen, water, helium, and hydrogen. And we've plotted two different things. We've got our molecular speed, how quickly they are moving at a given temp. That's going to be important here. So all of these particles, all of these gases are at the same temperature, at the same temp. And then on our kind of vertical axis over here, we have the relative number of molecules with a given speed. So it's kind of the total number of particles at that speed. And we've plotted speed across our x-axis going across the bottom here. So kind of we're comparing two things here. We're saying at a given temperature, how fast are they going and how many of them are at that speed. Let's look at a couple examples here, and hopefully that'll help us out. So we're looking at number 1. I'm going to keep from kind of scrolling up and down, I'm just going to kind of be referencing the chart here as we go. Number 1 says, what is the molar mass of our helium? Well, if we look on the periodic table, we can find the molar mass. I think it averages 4.00260, or from our graph, we know that each one of our helium particles has a mass of 4 AMUs, or grams per mole. Our molar mass, grams per mole. Hydrogen from the graph up above, we know it to be 2 grams per mole. Sorry, my handwriting is a little messy here. And oxygen from above is our 32 grams per mole. Now, if we're looking at those, just those kind of 3 particles, it's worth comparing here. So if we think about these 3 particles, our heaviest, and I think that's our next question, right? Which gas has the most molecules with the lowest molecular speed? And so if we're thinking about our graph, we're saying our speed is increasing as we go from left to right, with low speeds down to the left and high speeds over to the right. And so the further left we are on this graph, the slower our particles are going. The further right your average particles are, the faster they're going. So just as we compare these, it looks like our lowest molecular speed would be the one furthest to the left. That's going to be our oxygen. Oxygen has the lowest molecular speed on average. Cool. Number 2, part C says, as the mass of the gas decreases. So as we go from a high mass of 32 down to 4, so we're decreasing down to 2, what happens to the average speed of the molecules? Well, and I think that's all the way across the board, isn't it? As we go 32 to 28 to 18 to 2, as we go from left to right on our graph, our molar masses are decreasing and the speed is increasing. And this makes sense. To have the same amount of kinetic energy, the same kind of speed of motion, as your particles get lighter, they're going to be traveling faster. That our mass and our velocity are going to be an inverse relationship. And so here we're saying as the mass decreases, so particles get lighter, their velocity is going to increase given that the temperature is staying the same. Kinetic energy is held constant. So we would say for letter C that we would see an increase in the average speed of the molecules. 2D says, do all the molecules have the same exact speed? Well, I think as we're looking at our graph here, we have a bell curve. We have a bell curve where most of our particles for oxygen, for example, most of them, our highest peak is here at the top of that peak, but we have a distribution. Some particles are moving really slow. Some of those oxygen particles are moving really fast. And so we'd say that no, not every single oxygen in our sample of oxygen has exactly the same speed. There is an average kinetic energy. And so we would typically compare our highest peaks or our most prevalent particles, but there is an average to all these particles because we have a wide variety of particles and not every single particle would be traveling at exactly the same speed. Mathematically speaking, that is impossible when we're talking about billions and billions and billions and billions of these particles. Cool, let's take a peek at figure 2. And then we're going to be able to start to kind of compare and contrast them to see what's going on for our different species. So in figure 2, again, just looking at my graph here, we're looking at our units. We got this funky little U-biz, but the units are meters, little m, meters per second. So meters being distance over time, that is going to be our velocity. Talking about the speed, it was kind of ACT style practice when we're looking at our units that we're describing. On the left-hand side there, we've got the relative number of molecules with speed u. So here we got relative number again. So we're just looking at how many particles are traveling at a given speed. And here, if we're looking at kind of our different measurements, here we've got Kelvin, which measures temperature, and we're looking at the relative speed of our nitrogen. So just analyzing our graph a little bit, looking to see what we got. And so now we can go down to 3A. 3A says, what characteristic is the same or is held constant for this particular piece? Well, I think the velocity is changing. And with that, so is the number of relative particles. Temperature is changing. The only thing that I think is being held the same here is the gas. And that in turn would be, if we think about figure 1, would be holding the mass constant. So for 3A, what's being held the same? Well, it's the same particles and therefore the same mass. For each of our little nitrogen molecules floating around in there, we know that nitrogen on average is 14. Each one's going to have a mass of 28 grams per mole. So the molar mass or the mass of each particle is the same, held constant. Cool, 3B says the average speed of the particles is represented by this little U symbol. What are the units on U? Oh, we already got that. Boop, meters per second. It is measuring the velocity or the speed. C says as the temperature of a given gas increases, what happens to the speed of the particles? So as temperature increases, we see that our average particles get further and further to the right. Well, that means that their velocities increase. And you knew this, as temperature increases, the particles speed up. They move faster. They have a greater energy of kinetic motion, increasing kinetic energy. 3C says, as the temperature of a given gas increases, what happens to the speed? We just did that one, excuse me. As temp increases, so too does the speed. D says, as the temperature increases, what happens to the relative number of molecules at a given speed? So that's asking us about the peak of the graph. As your particles start to speed up and they have more and more energy of motion, we see a wider band or a wider distribution of their relative number of particles. And so we would say that our peaks have decreased as the temperature increased. The number of particles all at the exact same speed has decreased. We see a wider distribution of particle speed. So it would be decrease for 3D. 3E says at a given temp, do all molecules of the gas move at the same speed? This is going back to the same one we did on 2D. No, it's an average. It is the average kinetic energy. We have these wide distributions of the speed of our particles at a given temperature. And so we'd say that no, it is an average across all of our different particles. Cool 4 says figure 1 is showing the effect of blank on speed. Well, I think we're looking at the mass of the particles. In figure 1, all of our different particles have different masses. While in figure 2, we're looking at the effect of temperature on speed. And hopefully we're starting to see that relationship here. Let me kind of slide down so we can look at that. I don't want that. Cool. So figure 1 is showing the effect of mass on the speed versus figure 2, which is showing the effect of temperature on the speed of the particles. And if we're just thinking about our relationships, we would say that as your particles become heavier, as you have an increase in the mass, it is an indirect relationship. We would see those particles slow down. There is a decrease in the speed of the particles or velocity. Conversely, if we have an increase in the temp, if we heat up our particles, we see an increase in the speed of the particles. Hopefully we're seeing that represented by the data up above. Cool, armed with this knowledge, flip it on over, try those questions on the back. When we all get back together, we'll be taking a look, looking at questions and making sure we're doing okay on these types of calculations and problems.